These enrichments are meant to give you a little bit of perspective of how matrix vector operations, matrix operations, and casting in terms of matrix vector operations and matrix operations is important if you want to attain high performance. And then on the flip side, what this means is that it's very important to be able to derive algorithms that actually cast computation in terms of these operations, which is what a big part of this course is all about. For those who aren't that familiar with computer architecture, let me just give you the basics, and there's no need to panic. I actually know remarkably little about computer architecture myself, and I've managed to have a very fruitful career that depends on knowing exactly what I'm about to explain to you. Alright, so what you need to keep in mind is that computation, multiplies and adds are useful operations in our field, and data movement is not useful. So data movement is overhead, and it's often the movement of data between memory layers that actually is a cause for concern. And if we can just overcome that, then we can achieve extremely high performance. So what you want to do is you want to think about the memory hierarchy. And what does that mean? Well, think of it as a pyramid. Okay? In order to compute, you have to have data in registers. Only if data reaches registers can one compute with it. So inherently one must bring data into registers. And what are registers? Think of registers as extremely fast memory, but you have extremely little of it. Okay? Think in terms of 16 to maybe 128 or something like that. Let's not get into the details of that. A small number. On the other extreme is main memory. These days there's lots of main memory. You can put huge matrices there. After all, we're interested in computing with matrices, and they can be stored there, and main memory is relatively cheap. Okay. Now, the problem is that main memory is extremely slow, while once you get data into the registers, accessing the registers is extremely fast. It better be, because if you can't get the data out of the registers fast enough to compute with it, then why bother having really fast compute units, right? So, now, main memory is extremely slow, registers are extremely fast. Now let's take a typical operation that we ran into during the course. Let's say that we want to do an XP operation, which we will indicate by a vector plus equal some scalar times a vector. Okay, so we're going to take a scalar times a vector and add that to the vector. If this vector is of size n, then of course this vector is of size n. Notice that inherently these vectors have to be brought into registers, and therefore inherently you're going to have to, if this is y plus equals alpha times x, inherently you're going to have to read x, that's n memory operations. You have to read x, you have to read y, and you have to write y back to memory. So in total, 3 n memory operations must happen. And if initially the vectors are in main memory, and when you're finished they have to be in main memory, then notice that that's a lot of data movement, especially if you take into account that with each pair of entries in the vectors, all you do is a multiply and an add. Okay, so in the end you do 2n floating point operations. Typically in our field we don't really operate with integers, we operate with real numbers, but those are represented as floating numbers. Okay, now, no matter how fast you do these floating point operations, you've got a problem because you have a proportional number of memory operations that must be performed. And if that's really slow compared to performing the floating point operations, that's a problem. Now, How did people try to overcome the fact that main memory is extremely slow? Well, they introduced something called cache memory. And what is cache memory? Cache memory is a very small amount of very fast memory. So close to the registers is an L1 cache. And then over time they have introduced L2 and L3 caches as well. The L1 cache is small, the L2 cache and L3 cache get progressively larger, and then eventually main memory is very large. Now, do these caches actually do us any good? So the idea is you can take data out of main memory, store it in, say, the L1 cache, compute with it much faster because data can be brought into registers from the L1 cache much faster than from main memory. And then hopefully everything is fine. The problem is that if our premise is that we initially start with our vectors in main memory and we want to end up with those vectors in main memory, then having a very fast L1 cache doesn't really do you much good, because inherently these vectors must be brought in from main memory into the L1 cache, and you still pay the price of bringing it out of the main memory and back into the main memory. So it doesn't do you much good. That's where all the cost is. Okay, well, fortunately, we learned about matrix vector operations, and we learned that matrix operations could be cast in terms of matrix vector operations when we do unblocked algorithms. Does that do us much good? Well, think of the matrix vector multiply. A vector is updated by a matrix times a vector, and let's assume that this vector is of size n, as is this vector, which then of course means that the matrix is an n by n matrix. So now we're doing y plus equals a times x. Well, inherently, every entry in the matrix must be brought into the registers. Okay? When you think about it, when you perform a matrix vector multiply, you do a multiply and an add with every entry in the matrix. What does that mean? Well, if it's an n by n matrix, then you inherently have to do n squared memory operations. And what we just said was that every entry in the matrix is used for a multiply and an add. If we count those separately as floating point operations, then inherently we end up doing two n squared floating point operations. And notice that we're still doing one memory operation for every two floating point operations. And again, if memory operations are extraordinarily slow, we still haven't come out ahead. Well, we come out ahead a little bit, because notice that we could take our vector x, store it in the L1 cache, and then keep it there during the entire matrix vector multiply, and that saves us some memory movements. But ultimately, we have to do one memory operation for every two floating point operations, and that's a problem. Okay? Inherently, the cost of moving the data between in and out of main memory is the problem. Might a rank 1 update be better? Well, there you have a matrix that you update with an outer product. But if you think about it, because you're updating the matrix, you have to read that matrix and you have to write it. There are n squared entries again, so that means now that we have to do two n squared memory operations. And if you think about it, for every entry in A you have to do a multiply and an add. You may have to go back and review what a rank 1 update is. And therefore we're still doing two n squared floating point operations, so we notice that we actually are worse off. Right? Before we had one memory operation for every two floating point operations for matrix vector multiply. Here we have one memory operation for every one floating point operation. That's worse. So you could say, well, at least if we can come up with algorithms that cast most computation in terms of a matrix vector multiply instead of a rank 1 update, then our memory movements have been reduced by a factor 2, and then actually we do a little bit better. So you're already starting to learn that finding different algorithms that cast computation in terms of different other algorithms is a good thing. Still, anytime you cast computations in terms of what we call matrix vector operations, you're probably not going to get particularly good performance unless it happens to be the case that all of that data is already sitting in a cache somewhere, or unless it happens to be the case that the computations that you do actually is a very small fraction of the total computations that you're having to perform. Okay? Now, you could just say, well, that's just tough luck, that's just the way it is, let's just go home. Well, you could say that, but actually we can do much better. What if we have a matrix-matrix multiply sitting in main memory? Well, then we have a matrix C that's being updated by the product of two matrices, C plus equals A times B. Okay, if you paid attention, you notice that the matrix-matrix multiply can be implemented as a matrix vector multiply for every column of B. And what that means is that the number of operations that you need to perform is, well, if each of these matrices is n by n, the number of operations that you need to perform is inherently 2 times n cubed. A matrix vector multiply is 2n squared floating point operations. A matrix-matrix multiply is therefore 2n cubed floating point operations. So now we have an operation where we perform 2n cubed floating point operations. What is a lower bound on the amount of data that inherently has to flow across this boundary, which is where the problem is? Well, you have to read A, you have to read B, and you have to read C and write C back out. So that's n squared memory operations plus n squared memory operations plus 2n squared memory operations. So that means 4n squared memory operations. There's an opportunity here to say we can amortize the cost of memory operations over more floating point operations, because the ratio here really is 2 memory operations for every n floating point operations. Okay? Now, that is what would happen if you could take these matrices, cram them into the L1 cache, do a bunch of computation, and then eventually write them back out. The unfortunate fact is that these matrices tend to be larger than fit in the L1 cache. What is the solution? Well, you learned about slicing and dicing. The solution is to somehow partition these matrices in a way so that you work with smaller subproblems that actually fit in the various caches. Now, how to slice and dice this so that you can get extremely high performance, that is the topic of the next video.